Hi, y'all. This is Blasky. Today we're going to talk about topic 3.7, which talks more about what is going on with the motion of the gas particles, now that we've already talked about the mathematics of describing their sort of larger macroscopic view of their pressure and their volume and their temperature. Now we're going to zoom in a little bit and talk about those individual particles themselves. So we have this theoretical set of assumptions that we can make about gases. And we call that the kinetic molecular theory, or the KMT. And these four assumptions have to work for us to be able to explain what's going on with these particles. Now, again, these aren't perfect, but they are the assumptions that we make to be able to function with these gas particles. So first assumption is that all particles are in constant random motion, which we know to be true about gas particles. We've been talking about that before. Assumption number two is that the collisions between the particles are perfectly elastic. Elastic here is the physics definition of elastic, which means that those particles bump into each other and do not transfer or lose. They can transfer energy, they do not lose any energy as they bump into each other. So they bump, they keep going their own way, and they have not lost any energy. Assumption number three is that the volume of the particles in a gas are negligible. We talked about this when we talked about the assumptions we had to make to talk about ideal gases. And number four, this is something new. So the average kinetic energy, or the movement energy of the molecules, is proportional to its Kelvin temperature, meaning that if we increase the temperature, then the average kinetic energy, or the motion of those particles, are going to increase. Notice again that we are assuming that we do not have any intermolecular forces acting. We're assuming we have ideal gases. And we're also assuming that gases expand to fill their container, which we know that they do. So taking in these four assumptions of the kinetic molecular theory helps us explain theoretically why gases behave the way they do. So Boyle's law talked about the relationship between pressure and volume. So if we think about this kinetic molecular theory and its assumptions, this helps explain why Boyle's law happens. So if the volume is decreased inside of the container, that means the gas particles are going to hit the container more often, thus increasing their pressure. These are explanations that you could be asked to use on a free response question. Charles' law showed the relationship of pressure and temperature. So this also can be explained using kinetic molecular theory. So when we heat a gas, we increase that temperature, we're going to increase the kinetic energy of those particles, making them move faster, and thus they're going to hit the walls more often and with more force, which is going to increase the pressure. The only way to keep the pressure constant is to allow the volume of the container to increase. Here we go. Here's Gay-Lussac's law also. So again, if we increase the temperature of those gases, the speed of its particles are going to increase, the kinetic energy is going to increase. If the volume is going to be forced to stay the same, then that means that we are going to increase our gas pressure. And it even helps explain Avogadro's law. If we have an increase in the number of particles to stay at the same temperature, just adding more particles is going to increase the pressure, because now we have more particles able to bump into that container. In order to keep that pressure constant, we would need to increase the volume to allow that pressure to stay constant. So one of the ways that we can account for especially the energy of these particles as we change the temperature is this fancy looking graph called a Maxwell-Boltzmann distribution. And we're going to use this type of mathematical representation several times throughout the year. The important part to understand about these graphs, and this one sort of is skewed a little bit, so it's hard to imagine this, but the length of this line is going to be constant for any sample of gas. But as we change the temperature of that sample, we are moving this outward point and allowing that line to spread out a little bit more. But what is always going to be true is that the area under this curve is going to be constant. So whether I'm at a low temperature or at a high temperature, the area under that curve is going to be constant, meaning that the total number of particles we have in that sample is going to be the same. But what Maxwell-Boltzmann shows us is that if we change the temperature of our sample, we change the velocity of our sample. Now, we don't change the velocity of every single atom, but we change the average velocity. So if we look at this maximum, if I have 273 Kelvin, notice that along my x-axis, I've got velocity. My y-axis, I have number of particles. So the majority of my particles have a velocity of, what is that? 400 maybe? 400 meters per second. Now there are some particles that have a lot higher velocity, some particles that have basically no velocity, but the majority of them at that temperature are around, well, we're going to say that that's 400. Now if I increase my temperature to 1273 Kelvin, now the majority of my particles now have a velocity of around 1,000 meters per second. Are there still some particles that have only a velocity of 400? Yes. Are there still some particles that have a velocity of almost zero? Yes. Our maximum velocity has also increased though. And then as we increase our temperature even more, we increase our average to 1,500, 1,400. Again, we're increasing our maximum velocity, but our peak is flattening out, right? So we are spreading out our velocities more. We don't have that super high concentrated number of particles at a smaller range of velocities. We have a larger range of velocities that go up to a higher velocity, but that information gets more spread out. So this helps us show that the Kelvin temperature is proportional to the average kinetic energy. As I increase my temperature, I am increasing my average kinetic energy and increasing my velocity of those particles. Kinetic energy is related to velocity. By this equation, 1/2 mv squared, that is also on your equation sheet. Some other information that can be affected by temperature and by kinetic energy: smaller gas particles have a faster velocity than larger particles if they're all at the same temperature. If we are at the same temperature, that means those particles have the same average kinetic energy. But if their mass is smaller, then their velocity is going to be bigger. So for example, if I have hydrogen gas H2 and I have oxygen gas O2, both at 273 Kelvin, that hydrogen gas is going to have a higher average velocity than the oxygen would. They're still going to be the same kinetic energy because they have the same temperature, but because those hydrogen atoms are smaller, they're going to move faster. And then if we increase the temperature of any gas sample, the motion of the particles is going to increase, increasing the velocity of those particles because that kinetic energy is going to increase. Like I said, these graphs are going to show up several times throughout the year as we're talking about motion of particles and how things change with temperature. So we'll get pretty used to seeing these. That's the last thing we're going to talk about gases for right now. So I'm going to sign off and I will see you all later. Bye.